Okay. Do you want to get started, Alex, or do you want to keep waiting?
I don't think we should keep people waiting because they've all showed up on time. So, yeah. Yeah, why don't we get started? I'll figure it out.
Okay, sounds good. Maybe he'll join partway through. It'll be great. Okay, so welcome everybody to another IR Science Interest Group or IR-SIG webinar series. I'll be moderating the webinar today. My name is Meredith McGregor. I'm one of the co-chairs of the IR-SIG along with Mike Zemkoff, and I'm also an assistant professor here at the University of Colorado Boulder. Before I start a speaker, I'll start with just a few instructions on how this will work. I know we're all really familiar with Zoom, but it doesn't hurt to go over a few things. I've also typed these into the chat window so you can refer to them there. We'll have a Q&A period at the end of the talk, but that does not mean you can't submit questions during the talk. So please use the chat freely to submit questions. You can also submit to our speaker. You can submit them to the Leadership Council. Any technical difficulties, all of that should go in the chat window. If you haven't found the chat window yet, if you go to the bottom of your Zoom window, there's a little button right in the middle that says chat. And if you click on that, that will bring it up. So please type your questions as they come up into the chat. If you would like to ask a question yourself directly to the speaker, then you can use the raise hand feature also at the bottom of the Zoom window. So if you go to the bottom and you look for reactions, there's a little smiley face with a plus sign, and you click on that, there's an option to raise your hand. And during the Q&A, if you raise your hand, then I will unmute you and you can ask your question directly to our speaker. Again, questions for Leadership Council, put in the chat window. I'll try and get to those at the end or send you an email later. You can report technical difficulties. Hopefully, fingers crossed, we don't have any. And the last thing is that this is recorded and will be available to view later on our webinar webpage. And I've put the link for that into the chat as well. And I think Min has joined. So I have the perfect length introduction. So with that, then I will introduce our speakers for today. We have two speakers. First, we have Dr. Alexandra Pope, who is a professor at the University of Massachusetts Amherst and is the Deputy Project Scientist for Toltec and an LMT US Open Access Program co-PI. And just joining us as well is Dr. Min Yun, also at UMass Amherst, who is the UMass Project Scientist for LMT and an LMT US Open Access Program co-PI. And with that, I will stop talking and I'll let you take it away.
Okay, great. I'm just confirming, Min, you're there. Can you say hello?
Yes, I am. Thank you for asking me the password.
You like to give me a heart attack. For everybody else on the line, I was also telling Meredith that right before this, I noticed that my laptop was down to 0 battery. It's been having the service battery for about a year, but it's fine as long as it's plugged in, and now it seems to be on the fritz. So anyway, let's hope the battery lasts, and at least I have my co-presenter with me today. So welcome everybody. Thanks for joining. The goal of this presentation is to inform the community about this new US community access program that we have on the Large Millimeter Telescope. And so as Meredith said, both Min and I are involved in this program, as well as several leadership roles within the LMT collaboration. And I've got the rest of our open access team written on the first slide here. I assume you can see the slides? Yes?
Everything looks good.
Great, awesome. Okay, so I'll start with a brief motivation of why do we need a millimeter single dish telescope. I'll provide an introduction to the LMT for those who don't know. We'll provide a sampling of LMT science results to give you a flavor of what sorts of things you can do with the LMT. We'll talk about 2 open access opportunities. So first is the Toltec legacy surveys. So Toltec is a new camera, which we'll tell you about, and those legacy surveys data will be public. And then the new open access program at the end. And so Min and I are going to be changing off. I'll get started first, and then I'll pass it off to him in a little bit. So just to start with the science motivation, I think it's preaching to the choir with this group here, the infrared science interest group. We all know how important the infrared is, but it's nice to remind ourselves with beautiful pictures like this, where we've learned a lot about planet formation, star formation, galaxy evolution. We've learned a lot about these processes from images like this from the Hubble Space Telescope, but we know fundamentally that this is only capturing half or even less than half of the information that we're getting from these processes. And so all of that remaining light we know is getting caught up in the infrared. And the most fundamental observation that shows this to us is the plot here showing the total power as a function of wavelength in the universe. So we can see the cosmic microwave background dominates by far. That's our relic of the Big Bang. But everything that's happening in terms of galaxy evolution, star formation, planet formation is coming out through the infrared and optical backgrounds. And you can see that those are two bumps, and they're roughly equal in power, shown as the integrated values here. And so what this tells us is that half the light that is emitted from planet formation, star formation, galaxy evolution gets caught up in the gas and dust in the interstellar medium and re-radiated at these longer infrared wavelengths. And so it's really important to probe these obscured phases. And half of the light may be caught up in the dust, but even more than half is caught up from star formation specifically. And that's because stars are formed in these dusty cocoons of gas and dust. And so when we make a measurement of the total star formation in the universe, so this is the classic Lilly-Maddow-Dickinson plot that shows the total amount of star formation forming in a volume of the universe as a function of redshift or look back time. And we measure how much is coming out directly from the unobscured star formation in the ultraviolet, shown as these green and purple and cyan points, compared to what we trace in the infrared of the obscured star formation. You can see that it dominates considerably over the portion of cosmic time that we've had accurate measurements of the infrared. And what you can see here is there's actually quite a gap here where at the highest redshifts, we haven't had good enough infrared measurements. You can see the error bars are huge on this data point. We really don't have the integrated values to very low error bars out here. So we don't know how much this infrared component continues to dominate out to the highest redshifts. And when you break this down and you go and look at a given redshift, let's say redshift 2 here, and you look in galaxies as a function of their stellar mass. So here's the average stellar mass of galaxies and showing their average star formation rates. So this gray shaded region is the galaxy star formation main sequence that's been well established. Most galaxies, star forming galaxies, follow this sequence. You can then separate out that star formation into the components from the infrared obscured in red and the unobscured ultraviolet traced in blue. And you can see the highest mass galaxies are far dominated by the obscured star formation. And as you step down in stellar mass, the unobscured component becomes more important, but it doesn't draw even until down to a stellar mass of about log stellar mass of about 9.4. And so a lot of this is well below the knee of the mass function. And so most of the star formation is clearly coming out from this dust obscured phase. So I said it's important to observe in the infrared, and the millimeter is a component of this. The millimeter wavelengths, particularly here I'm showing Toltec 1 millimeter, nicely probe the Rayleigh-Jeans tail of a dust distribution. So here are two spectral energy distributions of a dusty star-forming galaxy at redshift 2 and redshift 6. I'm only starting in the infrared portion, so you don't even see the optical bump over here. You just start with these mid-infrared features. And so there's a peak in the emission, and then there's the Rayleigh-Jeans tail over here. So for a galaxy at redshift of 2, when you're in the Rayleigh-Jeans tail, these millimeter wavelengths are great tracers of the total dust mass of the galaxies. And as you shift the spectrum to even higher redshifts, redshift 6 or beyond, you start to probe the peak of the infrared bump, which is a very good tracer of the total infrared luminosity or the dust obscured star formation rate. So single dish submillimeter observations have been limited in the past to the most extreme galaxies. And here I'm showing a fairly extreme example because this is the first image that was taken at submillimeter wavelengths of an extragalactic field. This is the Hubble Deep Field dating back, 20 some years now. But this is still a really excellent example about how limited we are with these submillimeter observations. You can see there's half a dozen or so blobs in this image on the right, which is showing the emission at 850 microns. And each of these blobs is corresponding to maybe 1 or 2 individual galaxies in here, but making those associations is really challenging at these coarse resolutions. And this is because we're going to such long wavelengths, and if we're dealing with a single dish telescope, we just have to make it that much bigger to get the adequate spatial resolution. And so we run into confusion noise, which has hampered a lot of studies. And this has gotten better since the original SCUBA data in 1998 with Herschel, but we're still limited by beams of greater than 11 arcseconds for all single dish sub-millimeter telescopes currently. So we need a big telescope, or you might say, well, you can also do this with ALMA. And so we know the past 10 years have been a revolution with ALMA. ALMA has this spatial resolution and it has the sensitivity. And so, it's a really great tool to be able to go in and study the dust obscured star formation from individual galaxies. The problem is ALMA has a small field of view. And so here's a map taken with ALMA. So this was 20 hours on the Hubble Ultra Deep Field, and you can see there's about 16 robust galaxies in here, which you can very quickly associate to their optical counterparts because of the resolution. But this isn't a very efficient way to survey very large patches of the sky. This is just 4.5 arc minutes squared, and we need to probe large areas to overcome cosmic variance. So a better strategy then is to maybe take a single dish telescope. In this case, they used the Loboka telescope. And they did a survey over a large area, and then those blobs that they didn't have good resolution of, they then targeted those with ALMA. So here they spent 5 hours and did 100, they got 100 galaxies recovered. And so you can see here the positional uncertainty from the single dish measurement and then how ALMA is able to hone in on it. So there's a lot of synergy between these sub-millimeter single dish telescopes that can do wide areas fast, identify sources, and then ALMA can go in and do the detailed study. So there's been a lot of international efforts and recognition that single dish sub-millimeter astronomy is really important. 10 years ago, when we had the 2010 decadal survey, this was recognized with a strong endorsement for the CCAT telescope, which was going to be a 25-meter telescope in the Atacama. Since then, this project has evolved into CCAT Prime, which is a 6-meter sub-millimeter telescope being built down in the Atacama, but this is still under development, under construction. And more recently, the European community has developed this concept called ATLAST, which is going to be a 50-meter telescope that they'd like to put in the Atacama, and this is in the study phases. But we do have something now, and that's the large millimeter telescope. And so we'll tell you a little bit about that now. I'm going to pass things over to Min. Min, go ahead.
Thank you, Alex. So I think just scanning through the attendees, I think a number of you are familiar with the radio telescopes and large millimeter telescope. But in case you're not, let me point out some of the salient features of doing science in some millimeter wavelength. So the diameter, 50-meter diameter, means it's a really big telescope. And in the radio astronomy, detectors are detecting induced electric field. So collecting area is proportional to the sensitivity. And ALMA has about 3 times the collecting area. So that means at least a light bucket, LMT will be about 1/3 as sensitive as ALMA, but it's in the neighborhood. And also 50-meter diameter will impact diffraction limit of angular resolution, which will be important for some of the reasons Alex was talking about. The location of the telescope is Volcan Sierra Negra near in state of Puebla, Mexico. I'll show you in the next slide what that means and what that impacts in terms of doing science. Because it's a 50-meter diameter metal structure, our biggest enemy is actually gravity. So we're trying to steer this Olympic-sized swimming pool and move it and control it to accuracy of an arcsecond on the sky. So that requires enormously sophisticated robotics. And we have actually fully active surface to combat the effect of gravity. And at the moment, our instruments operate between the wavelength of 1 to 4 millimeters, which translates to diffraction limited angular resolution of 5 to 18 arcseconds. The field of view is only about 4 arc minutes. This is because it's a 30-year-old optical design. If we designed LMT today, it would be much bigger. But if you think about the resolution, this and the number of pixels we can put on the sky, this is actually more than adequate for a number of things we can do. And I'm going to show some of the examples of what all of these things translates into science shortly. So first, the location. As you can see on the left plot, LMT is located just about 200 kilometers east of Mexico City. So if you land at Mexico City Airport, you can actually, there's a highway that connects Mexico City to Veracruz, and we can be on the telescope on the mountaintop within 5 hours of landing at Mexico City, assuming you're not stuck in the immigration for a long time. And the picture on the right shows the two mountains that are relevant to us. The one on the left is Pico de Arizaba. It's an almost 19,000 feet high mountain. It's the tallest mountain in Mexico. It's actually a national park. The peak on the right is Serra Negra, where our telescope is located. Actually, these two peaks define the national park. So we're inside the national park and we sort of operate the national park ourselves. The height of the mountain peak where the telescope is located is about 15,000 feet. So 15,000 feet is actually 1,000 feet above Mauna Kea, although it's 1,000 feet below Alma site. So it's very high site, and we take all the precautions and advantage of the high altitude. The latitude of the telescope is plus 19, so it's almost exactly identical to Mauna Kea. So if you're thinking about sky coverage and sky coverage from Mauna Kea, that's pretty accurate. And we overlap with, in terms of sky coverage with Alma over something like 70% of the sky. So that's actually a much more a complete overlap and common science targets. And the next slide shows the opacity measurement at our site. And basically during the winter time, the dry season for us, we have a seasonal site between October and April. Median opacity at 225 gigahertz is about 0.1 or 2 millimeter of precipitable water. That's quite respectable even for almost standard. So during this winter dry season, the winter time, it's actually excellent sub-millimeter site. And even the daytime, it is actually quite good. So we are thinking about expanding our operation hours into the daytime. Even the wet season, actually, it's an excellent 3 millimeter site simply because we're so high in elevation. Next slide. And we had quite a bit of time to characterize the telescope and the instrument performance over the years. So we have all kinds of data to back up its performance. And a lot of this information is available on our website, which is listed on our last slide if you want to go check it. But basically, we have a pointing accuracy of about better than 3 arc seconds on dead reckoning anywhere in the sky. With the reference pointing on a nearby quasar, we can point to better than 1 arc second accuracy. The middle plot shows essentially effective collecting area as a function of frequency, which folds into all the efficiencies and whatnot. So we compared the effective area of LMT, 50-meter LMT, which is now, compared to a 30-meter, and you can see that at all wavelengths, we're roughly a factor of 2 better until we get to very high frequencies. And we actually have room to improve on that. So we'll continue to improve this plot as we move forward. And I mentioned about the importance of active surface. We have to maintain basically all panels across the 50-meter diameter to better than 100 micron accuracy, keeping the wavefront to within 100 micron or better. And in fact, we do. So the gain of the telescope between elevation of 25 degrees to 85 degrees is actually perfectly flat. So we demonstrate that through a number of measurements. So you can read about that in our webpage if you want more interest in that. For the program that we're talking about, these are the suite of instruments that are available for you to use. The Toltec instrument, which isn't physically at the telescope yet, but we're in the process of shipping, that's going to be our primary continuum imager. There are a total of 7,000 pixels, and there are 3 separate bands. We have detectors at 1.1 millimeter, 1.4 millimeter, and 2.1 millimeter, or in gigahertz if you're like in physical units. And we're in the process of shipping them. And as soon as the telescope opens, when the COVID situation in Mexico improves, we will be able to commission it and start doing some science. We're optimistic that'll happen this fall. At the telescope, we have several heterodyne spectroscopic instruments already, and I'll be showing some science results from those shortly. One of the workhorse instrument is, and a very unique instrument that we have is the ultra wideband instrument called Redshift Search Receiver. So it is one of the common modes of using ALMA is doing spectral scans through 1 or 3 millimeter window and trying to detect CO lines from distant universe galaxies. Well, we actually obtain spectrum of the entire 3 millimeter window using this instrument without any retuning in one shot. So this has been a very interesting instrument for us to use with a spectral resolution of about 3000. And then we have Sequoia, which is the 3 millimeter heterodyne imaging camera that operates in the 3 millimeter window with 16 pixels, and I have some examples of that. B4R and 1 millimeter receivers are basically copies of ALMA band 4 and band 6 receivers. So you can actually do spectroscopy in higher frequencies that matches ALMA bands. And we're in the process of completing a 1 millimeter array camera called Omaya, and we'll install that and operate it in the late this fall or perhaps more likely early next year. Okay, so to give you a little better sense of what these instruments are, I'm going to show some examples of science results that came out from some of our early science operation. So because it took us I mean, 50-meter diameter telescope takes a long time to build. So in the early 2010 or so, we decided we'll just pause the construction, do some early science so people will get the taste of what the telescope can do, and then complete the 50-meter construction. So we operated LMT as a 32-meter telescope for about 13 months between 2014 and 2017. It resulted in a number of publications and PhDs and master's thesis and undergraduate honors thesis along the way. And then we completed the surface in 2018 and went into a full science mode until COVID hit us. So in the next slides, I will highlight some of the variety of science we've done. So the first result I'm showing here is a paper by Miguel Chavez, who is a project scientist in Mexico, and he's a stellar astronomer. So his use of the LMT is this continuum imaging of protoplanetary disks in nearby stars. So there are 4 sort of extremely well-known protoplanetary systems among the nearby stars discovered by IRAS. So Epsilon Eridani is one of those well-known stars, along with Beta Pic and Vega and others. And in this case, the images you see here are historical images of the some millimeter continuum obtained by Scuba 2, and different instruments on different facilities. And they all look sort of a circular disc-like structure, about 60 astronomical unit in diameter, roughly the size of the solar system, which got people very excited. And this is the start of what's really dominating the use of ALMA today, and the really exciting science on protoplanetary systems and planet formation. One of the puzzles of these sets of observations was that these rings were not complete, and they were lumpy and asymmetric. So people had all kinds of interesting dynamical models to explain these asymmetry and the shapes. But when we went to LMT and used the Aztec instrument and imaged this field, what we found is much more uniform ring. In fact, we have models of the, Miguel has models of these structures, and he basically finds that there's it's essentially a uniform continuous ring or a disk. We also detect a structure associated with a central star. But in addition, because of the depth of the observing, depth of the data, we find all these background sources, which to me are essentially background submillimeter sources, but it has actually important implication, it turns out. So when Miguel compiled all the information from existing historical data, what he noticed is that this ring structure travels with a star at stars' proper motion, but the background sources stay. So the asymmetry that people noticed in their early observations and try to model, turns out there was blended structure from the background structure rather than the ring itself. So there are lots of interesting analysis done on this particular set of observation and historical analysis by Miguel, and I invite you to go look at that paper. Next slide. And this is a more recent 50-meter diameter LMT result using the Sequoia instrument, which is a spectral imager. As a demonstration science, we observed M51, which everybody knows what it should look like. So the picture on the far left is a CO1 to 0 map at about 14 arcsecond resolution. It took us only about an hour to produce this map of molecular gas in M51. The center panel shows a map of higher density tracer HCN, and it sort of mimics, but HCN is much fainter, typically a few 3 to 6% of the CO in terms of the peak brightness, because dense gas filling factor is much lower. So this was a demonstration of simultaneously observing different lines and looking at the line ratios. And on the right plot, this sort of the gross difference between the two tracers is shown. But really interesting science result is coming in the next page. Here, what Mark Heyer, who was leading this project, is doing is looking at the ratio between the dense gas to dense gas, meaning density of 10 to the 4 and above, to more diffuse molecular gas with density of 10 to 2 to 10 to 3. But here, breaking up geometrically, and then looking at the spatial dependence. So in the blue region, which is the nuclear region, he finds that dense gas fraction is much higher, about a factor of 2 higher. So on the histogram on the bottom shows that the ratio between HCN to CO line interval. So the blue shows in the nuclear region, the HCN line is about a factor of 2 higher. And then he's asking the question, does the dense gas fraction change within and outside the spiral structure? So you break up the regions that are associated with the spiral arms and the interarm regions. And interesting and somewhat surprisingly, basically he's finding that there is no dependence on dense gas fraction between arm and interarm region. So he concludes that the spiral density wave somehow does not play a role in dense gas fraction, which is not what most people have expected. It's work still in preparation, but I think it's one of the more interesting results that came out of LMT in a recent history. Next slide. This is a set of plots. This is a demonstration how the Redshift search receiver is used to great effectiveness. It's the program I'm leading, and the paper by Kevin Harrington, who was an undergraduate at UMass and did the honors thesis on this project. And recently he finished his PhD at the University of Bonn, and now he's an ESO postdoctoral fellow at ESO. What we did is we were trying to find the most luminous galaxies in the universe as a laboratory for driving mass buildup and the black hole growth in the early universe. And we did so by looking for dusty galaxies in the Planck database. So out of about 100 candidates we identified in the Planck database, we identified the individual targets using other information. And then using Redshift search receive on LMT, we determined their redshifts by detecting one or more CO lines in these galaxies. So they range between redshift 1 and 3. We have about 30 candidates so far, and these are follows up and comparison of CO lines from LMT, which in yellow, and then following them up for confirmation for 1 to 0 line using the GBT, which are the red lines. And on the next slide, this is an example of following up those same sources using the band 4 receiver that NAOJ in Japan has built and donated to us. And these are essentially demonstration science observations of the same sources. B4R has much higher spectral resolution, so you can see the details of the spectra better. You can see these asymmetric lines, which we later on found out using ALMA that these are obviously strongly gravitational dense sources. Their apparent star formation rate ranges from 7,000 solar masses to 30,000 solar masses per year. And it turns out they're rotation is magnified by a factor of 10 or so. And this asymmetry is emphasizing that only certain parts of the rotating structure is strongly magnified. But these observations took only 5 to 10 minutes because these lines are so luminous. Okay, so here's an example of a use of redshift search receiver in a different way. So these are work put together by Jorge Zavala, who was until recently a postdoc with Caitlin Casey, University of Texas. Now he's a new staff astronomer at NAOJ in Japan. On the top example, he followed up a bunch of the high redshift candidate Herschel selected sources. And this spectrum on the top is redshift search receiver spectrum of one of those Herschel sources that turned out to be at redshift 6. And you see 2 CO lines and then one of the strong water lines from that object. And in 2018, when he published this paper, this was actually the highest redshift submillimeter source known, but there are now other sources like this detected and confirmed by ALMA. There is also a program, they looked at something like a dozen high redshift candidates, and in fact, many of them are turned out to be about redshift 4. So there's a paper reporting those results in the journal and in the final stage of refereeing right now. In the next slide. Some of those sources are selected because they had very red color, meaning they were peaking in the 500 micron band in Herschel. And what Alfreda Montagna, who was leading this program, did was to image them with the Aztec instrument at 1.1 millimeter. So on this 4-panel image, what you see are Aztec 1.1 millimeter images of some of these candidate objects, where in many cases he found these multiple sources. The big circle inside the square is actually the Herschel beam. So to Herschel, it looked like a single source. But when he imaged them with Aztec on LMT, they broke up into multiple sources. And at the moment, it's not entirely clear whether this is the result of a process that leads to these extremely luminous objects, namely mergers or large-scale structure, or just simply superpositions of random sources. And that requires a little more detailed follow-up. And in following some of these with redshift search receiver, some of them are shown to be high redshift sources. Here's an example by Alex. What Alex has been focusing on are using these lensing to study more normal galaxies in the early universe. So this is an example of Aztec observation of one of the frontier field clusters, where using the lensing model and Aztec data, Alex identified a family of objects that are from a high redshift. And the example on the right shows the determination of redshift using ALMA, a carbon-2 line at redshift about 4.3. And using the lensing model, it's a little awkward to have Alex there and explaining Alex's work, but this is an example of actually a low star forming object that's magnified enough that we can detect and study. So the intrinsic star formation rate of this object is about 15 solar mass per year. So it's more of the run-of-the-mill star forming galaxies at this epoch. But even in such object at redshift 4.3, 80% of the star formation is dust obscurus, which is a very interesting result. So the dust obscuration continues to be important at high redshift. So in this last slide example, Joyce Caliendo, who's an undergraduate student at UConn, did her honors thesis work on this particular galaxy with Kate Whitaker. This is a quenched high redshift galaxy at redshift 1.9. And the measurement is trying to determine the gas content, coal gas content in recently quenched galaxy. And they analyzed that it is one of the, essentially gas content is less than 6% of the solar mass. So the gas is gone within a few 100 million years of quenching. And by itself, it doesn't, upper limits are seldom very interesting, but in this case, it has important consequences on impact of quenching. So again, if you're interested, it's one of the recent papers, and I invite you to go look at those.
Great. Thanks, Min. You did a good job describing our paper.
Thank you.
So I'm going to take over and talk a little bit about some of the future opportunities that we have coming forwards. And I'll start with the Toltec legacy surveys. And Min already mentioned the Toltec camera, which is being shipped as we speak. We've already shipped parts of it. Parts of it have already landed in Mexico. The rest of it is going to be packed up and shipped imminently. And so that is definitely on the slate to be commissioned late summer, early fall, assuming that things continue to improve with the pandemic. So why do we need Toltec? Well, this slide here is meant to demonstrate the vast improvement we get, not only from the resolution from going from a smaller millimeter telescope that has an 18 arcsecond beam, this would be Herschel at 250 or a little bit larger than the Scuba 2 on the JCMT, to something with the resolution of the LMT. And you can see these blobby-like galaxies are now resolving out into multiple different galaxies, and you can pinpoint them very accurately. And so what do we need to be able to make these images? We need a big, powerful camera. And so Toltec is built for that purpose. So Toltec observes with 3 wavelengths simultaneously, 1.1, 1.4, and 2.1 millimeters. You can see the beam sizes here ranging from 5 to 10 arc seconds, depending on which wavelength you're talking about. Toltec has about 7,000 detectors over the 3 arrays, which is a huge improvement over the previous camera Aztec, which was just over 100. The mapping speeds are given down here that tell you sort of how large of a field you can image down to a given depth in a given hour. And we have a range currently because we don't know specifically how Toltec will perform at the telescope. If it performs as we expected, as Aztec performed, then we will reach the fastest mapping speeds. So the PI of Toltec is Grant Wilson. He's building it at UMass. I'm a project scientist along with Itziar Saga at Anawi. And so the Toltec is designed to fill the field of view, the 4 arc minute field of view at the LMT. It does simultaneously imaging and polarimetry. The mapping speed is 100 times Aztec, not surprisingly, just with the increased number of pixels alone, but also the sensitivity of the pixels is improved. It was funded by NSF through the MSIP program a few years ago, and we are commissioning it this fall. And this is still just a picture of it. I should replace this with, this is a diagram, not an actual picture. I should replace it with a real picture. So to demonstrate the vast improvement in mapping speed that you get with Toltec on the LMT, you can look at a plot like this, which is quite messy. So I'll walk you through this. So this is showing the map depth that you can reach as a function of area. So if you want to make really big maps, really deep, you want to be down in this bottom right corner. And here we've got basically the estimated confusion limit that we expect with Toltec drawn here at a given map depth. So even at 5 arc seconds, we're still going to reach confusion at some point. And then we've got some lines here diagonally showing the amount of hours it would take to integrate the given area that you've got. And so you can see here 1,000 hours, 100 hours, and these are areas of 10 square degrees and 100 square degrees out here. So Toltec can map 100, well, as we'll see in a second with the legacy surveys, it can map something like 50 square degrees all the way down to the Eulerg limit in 100 hours. And so that's one of the legacy surveys that I'll describe. So what does that mean compared to previous observations? Well, we have some ALMA surveys down here, different ALMA observations. We have a few Scuba 2 surveys shown up here as these data points. And so you can see how much we're improving both in area and depth from these previous surveys. And that's just because this camera is so powerful and it's on a single dish, a large single dish telescope. So when Toltec was funded, it came along with building the instrument and also providing some public legacy surveys for the community. So we promised to do at least 4 100-hour surveys, 2 galactic and 2 extragalactic, and we would make all the data public and we would define the surveys along with the public. And so what we did was we developed 4 working groups for these 4 surveys that are defined here. So an ultra deep survey of star forming galaxies, large scale structure survey, survey, clouds to core legacy survey, and fields and filament survey. So there was coordinators for each of these surveys that contacted the community and brought together the working groups. Anybody is welcome to join any of these working groups. So if you're just now learning about tool tech and you're excited by the science, please go to our website, and all you need to do is sign up to get involved in one of these working groups, and you will start getting all the emails and be invited to the meetings. So we held community meetings through webinars and also in-person meetings to really talk about what fields we wanted to do and what depth we wanted to do for these surveys. So I'll tell you what the plans are for those 4 surveys. So let me start with the large scale structure survey. So the goal of this survey is to really take advantage of the fast mapping speed and cover a wide area. Herschel did wide areas over large extragalactic regions, but it suffered from the resolution. So here, because we can do wide areas and our confusion limit is lower, we can do all the way down to the Euler limit, which is about 1 millijansky 5 sigma at 1.1. We're planning to cover about 50 square degrees, depending on the final mapping speeds. And the goal of this survey then, to do wide areas down to the Euler limit, is to really try to understand the relationship between the spatial distribution of these dusty star-forming galaxies and the larger scale structure that they're embedded in. So the relationship to clusters and protoclusters. In particular, we can take advantage of the 3 bands of Toltec to study the Siniaev-Zildovich effect. And so here's the fields that we've chosen here. The ultra deep survey of star-forming galaxies is going to the opposite end and pushing as deep as we can go, going all the way down to the confusion limit. So we estimate that's about 0.1 millijanskys 4 sigma. This is the detection limit, not the noise limit. So that's all the way down to the Lurg limit. So these are galaxies forming stars at about 10 solar masses per year. We're going to do almost a full square degree over a bunch of common legacy fields. And the goal of this survey is to fill in this gap here. So I showed you this plot at the beginning where we really don't know what's happening with the obscured star formation rates at the highest redshifts. And so Toltec should be able to really nail this down. And so these are just a few graphs quantifying those 2 extragalactic surveys. So this is showing as a function of redshift, the limiting infrared luminosity that we get down to. And this is just to demonstrate with the ultra deep and with the large scale structure, this negative K correction that we get at millimeter wavelengths, because you're climbing up the Rayleigh gene's tail as you push the galaxy to higher redshifts. You are equally sensitive to a dusty star forming galaxy at redshift 7 than you are at redshift of 2. And this is plot on the right is showing the histogram of the number of galaxies that we expect to detect in these 2 100-hour surveys as defined for these areas. So we're looking at 100,000 millimeter detected sources, which is new parameter space, new statistics that we haven't had. So moving a little closer to home, we've got 2 galactic legacy surveys. So the first one is the clouds to core survey. So this survey is really about understanding star formation when you go from the molecular clouds to these dense cores that are going to form stars. And in particular, they want to look at the link between the core mass function and the initial stellar mass function and look for variability in that. And so in order to do this, you need a complete census of cores in nearby clouds. So they've designed a survey where they're looking at 10 clouds, and within these 10 clouds they expect to find thousands of cores which will be spatially resolved with the resolution that we have. They're all within 1.5 kiloparsecs. And here's an example of the science you can do here in terms of measuring the core mass function. You can see different predictions for different mass functions here. Here's a limit that was put from a previous Aztec survey on the LMT in early science mode. Here's a deeper limit in slightly later Aztec data, and here's where the cloud to cores survey is going to go down. So it's really down deep enough in the core mass function to be able to probe variability and differences here. And then, sorry, this one pops up a bunch. I'm not used to these pop-up stuff. The second galactic legacy survey is fields and filament legacy survey. So this is really aimed at using the polarization capabilities of Toltec to try to understand the role of magnetic fields in regulating star formation. And this survey is designed to probe the magnetic fields over a wide range of scales from 0.001 to 1 parsec. And so some of the different scales that magnetic fields are acting within cores and clouds and filaments are shown here. I'll just flip to the next one, which lays out their survey. And so the key questions that they want to answer with this survey is the relative importance of magnetic fields, turbulence, and gravity, and regulating fragmentation. How does the magnetic field affect the transfer angular momentum during gravitational collapse? And what controls the efficiency of dust grain alignments with respect to magnetic field? So in order to do this, they're spending their 100 hours, the coordinators are listed here, imaging 6 molecular clouds. And you can see some pointings here with different resolutions shown, the resolution of Toltec at 5 arc seconds here. And then on the next slide, this shows the montage of the 7 fields that they've chosen with the planned imprint for Toltec. All right, I'll pass it back to Min, I think, for this part. Go ahead.
Okay, so I think those legacy surveys are super exciting in the transformational science that people will do with using Toltec instrument LMT. There are actually additional possible programs that are coming along. So even if none of these are directly impacting your science, you should think about, how your science will be impacted by new programs and sign up and direct that conversation that way. But as a more general access to the LMT, we proposed to NSF that we'll get some funding from NSF to open up some of the LMT time to the US community users without any restriction. And with the funding, we'll provide the scientific support that is needed to carry out those sciences. So at the moment, LMT is operated by INAUE, which is an institute in Mexico, and UMass Amherst. We have 30% of the time, but we're going to allocate half of that time to the US community. Next slide. And what we propose there is make the time available. We construct a transparent and equitable review system, proposal and review system for everyone involved. We also have the data reduction pipelines and documentations and the help desks so that you can use the LMT as a non-expert modeling after ALMA, basically. It's not going to be ALMA because we don't quite have the ALMA budget, but we do our best to make your science available. Since we're a little tight for time, we'll just go to the next slide. And the big emphasis in NSF MSIP grant is that we try to make this use of the LMT as easy as possible. So we're hiring some new people to serve as the help desk and guide future users. And also we are teaming up with the University of Maryland team to make the data reduction pipeline and data archive, which is make it much more accessible to the users, including reduction of all archival data collected by the LMT and make them available to any archival analysis to scientific users. Next, okay, so we had one short call for proposals because when the pandemic started and we didn't know what the time scale was, knowing when the Toltec is coming along, we thought we would offer a 6-month period of time where people could use the Sequoia instrument, and we are perfecting the system for US Open Access program. And we only offered a spectroscopic instrument for that. And I think the results of the outcome is shown here. We received 75 proposals from the US and Mexican community. We offer 600 hours available time, and the request was actually 1,700 hours. So oversubscription was almost around 3. And the US community proposed about 1/4 of the time. And there's a breakdown of the US community proposal coming from 12 different institutions. Total available time for the US community was about 90 hours. The total request from the 17 proposal was about 200 hours. So oversubscription for this particular program, despite our webinars and whatnot, I don't think it was really fully realized. And it's actually considerably lower than ALMA, but I suspect this number is going to change once the words get out and the Toltec becomes available to the US community. But nevertheless, I think this is an important alternative for some or many of the science programs that you might have in mind. Next. So we are ready to release the next call for proposal. We're working hard on the lessons we learned from the first call for proposal, and we're preparing a release for the call for proposal sometime next month. This call for proposal will cover starting this fall, September, October. Again, pending the progress on the COVID situation. One big difference here is, I said, the Toltec will be available. We expect Toltec will be shipped and commissioned through the summer and hopefully through the summer and early fall, so that we can execute these science programs. And just to wrap up, sorry, I have a phone call, but
I can take over, Min. You can mute it if you want. Yeah. This is our last slide anyway. So we just wanted to finish with this slide and basically say that there's a lot of information through the LMT website, both about the telescope and the instruments, but also about the various proposal calls that we'll have, all the tools, the help desk. We did this webinar series. So in the fall, when we realized that we were going to be able to open this time, we decided the best way to interact with the community would to be host these webinars where people can ask questions in real time. We went over a range of topics to do with the telescope and the instruments and the proposing tools. And we've archived those all, so you can go back to those old ones. We are gearing up to provide some more webinars leading into the next call for proposals. And we also started a new email user list. So this is specifically for LMT users. And so we've added everybody from all of the other sort of ad hoc lists that we had in the past, and we're going to have a proper LMT users email list. And so if you'd like to be added to this, this is the best way to make sure that you get the announcement when the new call comes out. For now, you just send your name and email to Min. We're setting up a Google form to make that a little bit easier in the future. But that's all we had. So our main goals were to make sure everybody knows about these various opportunities for the community to use the LMT through the Toltec legacy surveys and also through these future proposal calls. So I will stop here and take some questions in the last few minutes.
Great. Thanks, Alex and Min. That was a really excellent talk. So to remind everybody, we have a Q&A period now. We have several minutes for that. And you can type your questions into the chat, or you can raise your hand, and lots of questions already. So I'll start with one that came in while you were speaking, Alex, in the chat, which I think is a sort of more specific question. It says, I signed up to get involved for the mailing list the other day, but never got a subscription confirmation email. Are we supposed to get one?
Is that for the Toltec or for the LMT? I'm guessing it's for the Toltec because it came in when I was talking about that part. Can you confirm? Is it for Toltec? Okay. Yeah. I will. It's possible that you do. I don't remember if you get a confirmation or you just get the next message, but I can check. I wrote down your name, so I will check for you and make sure and get back to you if not. But the website has worked in the past for just signing up and then you get added. So yeah, great.
Okay, and then Lynn, do you want to go ahead and unmute yourself?
Yeah, thanks. I was curious about the sensitivity calculations or estimates. Is there a chart somewhere that gives something, Millijansky's sensitivity per hour?
For a specific instrument?
I'm not even sure, probably
Okay.
Sequoia, I guess.
Yeah, there's a couple of slides that kind of flashed through there. The short answer is there are calculators for all of the instruments linked off of our main webpage. So that's the easiest way to use it. But we also have some graphics that demonstrate, like the Toltec one, mapping speed versus area. We have a similar one for Sequoia as well. I think we actually took that out because we didn't have enough time to talk about it, but we do have one for Sequoia as well. So yes, all of that information about the estimates is on the website.
Got it. Okay, I was looking around a bit while you're talking. If someone could type a direct link in the chat, that'd be great.
Sure. Yeah, I can check that after. Yeah.
I'll do that.
Thanks, Min.
Okay, Adam Ginsberg, do you want to go ahead and ask your question?
Yeah, so first I had the same question as Lynn. I just glancing around the website, I didn't find the calculators immediately, so it would be helpful to get pointed that way. But I also had a more specific question about with Toltec, have you guys measured or do you have a sense of what the largest angular scale recovery is going to be? So for those galactic surveys, merging the Toltec data with, say, Planck data or something, is that going to be possible?
That's a really great question. And we were just talking about that, I think, on our Toolkit telecon yesterday. Do you remember, Min, because they were talking about imaging some of the large nearby galaxies, and this came up.
Fundamentally, the footprint of the array is a spatial filter, but we have been working on recovering structures larger than the footprint using different algorithms, using Aztec first. And we think it'll be easier once we have this many larger mouthful, much larger field with many more detectors and better constraint on what the atmosphere does. But at the moment, we don't have a definitive answer. I think it's going to be a research project. So definitely we can do 4 minutes and perhaps substantially better. Well, let me add that we are actually developing a simulator for the data, I mean, entirely through the atmosphere and the time stream. So we are going to start working on seriously on recovering some of these algorithms probably as soon as this summer.
So I just put a link in the chat with the link to the calculators. I hope that goes to directly to them now. Yes, it does. So that's for the spectroscopic one. Someone pointed out Toltec is not there. So that's right. So this is actually really good feedback because, as Min said, we basically, pivoted from running this observatory just for like our local communities in sort of a small scale way to providing it for the whole, international community, well, national community. And so it's helpful to know where these sort of holes are. So I think, Min, we should make sure that the calculator link is more prevalent on the website because you have to link through the old call for proposals to get to it.
Good point.
Yeah. And so in terms of Toltec, I don't think there's a calculator for Toltec yet. All the mapping speeds are on the Toltec website. So I'll add a link to that in the chat as well.
Great.
So you just need the mapping speed. That's essentially the calculator, and those are all provided here. So I'll put that in.
There's another sort of question along these lines that came in the chat, which asks, what is the overhead for observations? So if you have, say, 1 hour on target, what is the total time that you need to be asking for?
That turned out to be a really difficult question. It depends on the instrument. The operating model is that, like ALMA, we will take care of the overheads. A lot of almost all observations is going to be done by Q observations, and a lot of the calibration is shared. So we will actually take care of that ourselves. The open time, the available time that is advertised are own source science time only. At the moment, in the last cycle, actually, that was not totally clear, and it wasn't clear exactly what you were asking for and what you were allocated. But we're going to make that much clearer in the next call.
Okay. Great. So we are at the top of the hour. If anybody has any last second questions they want to sneak in, I'll sort of kind of say a closing bit and pause for a second. I want to remind everybody that we have these webinars roughly every month. So please do continue to join us for future webinars, join our email list, which you can find on our website. And if you yourself would like to give a webinar, or you know someone who would give an excellent talk, please reach out to Mike or I, and we're happy to set that up. And then I think with that, I'll say thanks to Alex and Min for a really excellent talk and for handling many, many questions. And thanks to all of you for joining us.
Thanks very much, Meredith, for having us. And thanks everyone for joining.
Thank you, everybody.
Okay.